Okay, this is the last video of kinetic theory of gases. Kinetic theory of gases. And in this one, what I want to discuss with you is the real behavior of gases. So real gases versus ideal gas behavior. Ideal gas behavior. Now, so far we have discussed gases as if those are ideal, and I gave you the ideal gas equation, PV equals nRT. And that is true for the most part, but under some specific conditions, that behavior, that ideal behavior of gases changes, and that's what we are going to probe into. The first one that I want to talk about is what happens when the pressure increases. So as pressure increases, what happens? Let's say we have a container. We have a container which has some gas and it has a movable piston, and I have these molecules. Sitting in the sample of the gas. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I'm increasing the pressure. Okay, so I'm going to increase the pressure. I will still continue to keep the temperature same. I'm going to increase the pressure. That means the volume is going to decrease overall for the total sample. 4, 5, 6, 7, 8, and 9. And as I did that, if you compare the two pictures, you can perhaps see that the distances between the particles have decreased. They are closer together. They are pushed closer together. So what I want you to do at this point of time is recall that postulate from the kinetic theory of gases, where we said that the particle volume is much less as compared to the total volume of the gas, And basically what that means is that at any given point of time, you can just neglect the particle volume because it's just way too tiny. That is true for the most part. However, if you increase the pressure so much that now the size of the gas molecules and the total volume are pretty much in the same order, you will need to worry about that, and you will have to perform a volume correction. Now, in this curve that I have as the background, you can perhaps see this is a curve of molar volume. This is molar volume versus the pressure in atmosphere. So you can see the red curve, which is for ideal gas, and the green curve, which is for a specific case of argon. Those are coinciding. They are meeting up when the pressures are as low as perhaps like 100 atmospheres or so. And notice as we increase the pressure past a certain point, the two show deviation. So they differ from each other. They show deviation. Okay, so what this means that beyond a certain point, as we have increased the pressure so much that the intermolecular distance between the particles, when that becomes tiny, then the volume of the particle itself is going to occupy a significant portion of the total gas volume, and in that case you will not be able to just neglect that. So one can say, and as you can see over here, is that when the pressures are really low, then the molar volume of argon, like I discussed, they are coinciding, they are nearly the same. But as the pressure increases, the molar volume of argon, which is the green one, is actually deviating, and in this case it happens to be greater than the ideal gas. That means at higher pressures, the argon atoms themselves occupy a significant portion of the gas volume, and hence that makes the actual gas volume much higher than the one that is predicted by the ideal gas law. So one can anticipate that the ideal gas law, which is PV equals nRT, so one can say that volume is equal to nRT divided by P. But in this case, if we have to perform the correction for the real gas, we would have to say that volume is not just nRT divided by the pressure. To that, we will have to provide a volume correction of N times B, where B is the constant for the volume correction, and N is the number of moles of the gas that are present. This correction was provided by a scientist by the name van der Waals. And of course, you can perhaps envision that greater is the size of a molecule, greater will be the value of B. So one can perhaps see that if you have something like water, something like H2O. Let me erase parts of this. So if you have something like water, H2O, and if you compare the value of B, it's 0.0305, and if you compare that to, let's say, helium, the value for that is 0.02370. So depending on the size of a molecule or an atom, the value of B can be predicted. You're not supposed to memorize these. The values should be provided to you to do any calculations. So realize that for van der Waals real gases, if you were to find out the volume, you would say that volume is equal to nRT divided by P plus NB, or that V minus NB will be equal to nRT over P. So if you remove the volume correction, you will essentially end up with the volume of the ideal gas behavior.